Hi, I'm Judy Cole, the Executive Vice President and CEO of the MIT Alumni Association, and I'm delighted to welcome you to this web production of the MIT Alumni Association.
Welcome to the MIT Faculty Forum online edition. I'm Wade Roush from MIT's STS program, and today we're talking about gravitational waves. So since the news conference on February 11th confirming the detection last September of gravitational waves from a pair of inspiraling black holes, MIT faculty involved in the LIGO project have been celebrated at news conferences and receptions, but today we want to shine a spotlight on the network of MIT alumni who are also among the nearly 1,000 researchers who were involved in LIGO, are involved in LIGO, and 4 of the 1,350 co-authors of the paper that appeared just over a couple weeks ago, proving Einstein's theory of general relativity correct. Well, as if it needed any further proof, but we were all waiting for this one with bated breath. So I have a couple of instructions and announcements to run through. So this is an interactive forum. We encourage you to send us your questions, which I will relay to our panelists. And basically all you have to do is complete the simple form right below the live stream video window. So just type your questions in there and they'll come right to me. Alternatively, you can send us questions on Twitter. You just have to use the hashtag MITalum, and I'll get to as many of your questions as I can in the time allotted. We'll go to about 4:45 Eastern, 1:45 Pacific. So joining us today are fellow MIT alum from Louisiana State University, Stanford University, Syracuse University, and the California Institute of Technology. They are 5 of at least a dozen alumni researchers and faculty who have contributed all or part of their careers to working on the Laser Interferometer Gravitational Wave Observatory, a joint operation of MIT and Caltech. I'm going to tell you who is joining us, and then I'm going to hand the podium, so to speak, over to them so they can tell you about their particular parts in the project. So first to join us are Brian Lantz, 92, PhD 99, who is a senior research scientist at Stanford University, and Brett Shapiro, who was a 2012 PhD from MIT and is a postdoc at Stanford. Then we're going to hear from Joseph Giaime, 1986 BS and 1995 PhD from MIT, who is a professor at Louisiana State University. Then we'll hear from Joseph Betzwieser, 2008 PhD from MIT and a research physicist at Caltech. And finally, we've got Stefan Ballmer, 2006 PhD and an assistant professor at Syracuse. So it's an amazing cast. It's the largest group we've ever had assembled for one of these Faculty Forum online events. Thank you, all of you, for joining us. And I'd like to let, first of all, Brian and Brett talk about what they're up to and what their parts were in the experiment, and what's your work look like going forward now that the big initial detection that milestone has been completed. What's next for somebody who works on LIGO? So Brett and Brian, take it away.
Thanks, Wade. Yeah, so I'm Brian Lantz, and I started working on the LIGO project about 25 years ago as a Europe student, actually working for Joe Giaime building vacuum equipment. And since then, I've been doing some work on sort of fundamentals of interferometry, looking for the precision with which you can measure something using photons. And then more recently, as the lead scientist for the seismic isolation and alignment system, which, as my mother-in-law says, is a big machine that doesn't move. So all of the optics for advanced LIGO sit in the vacuum chambers on these big seismic isolation tables. And I'm sort of the lead scientist for building those tables, working on the control laws for those, making sure that those things run reliably. No.
Great. Brett?
Over to you, Brett.
Yeah, so I'm Brett Shapiro, and I started working on LIGO as a graduate student when I got to MIT in 2005. And I worked on the quadruple suspension system that supports the LIGO mirrors, basically making them work. I built the prototypes, and I worked on the control laws that make them behave the way we want them to behave, and the the modeling so we understand how they behave. And I still do a little bit of that now, but now as a postdoc at Stanford, I spend more of my time thinking about what comes next after advanced LIGO. So in the future, we're thinking about making the LIGO mirrors cryogenic to reduce their thermal noise. And I work on ways to, I work on the engineering to make that happen, to make the mirrors cold without compromising all the other things that LIGO needs to have work properly, like the vibration isolation.
Okay, great. That's a perfect place to start. So, Joe Giaime, why don't we go to you next?
So what I do now is I'm in charge of LIGO Livingston. So we're one of the 2 observatories that has to run the detector around the clock and make sure that we're able to make a detection when it happens, and we understand our detector well enough, and we are staffed around the clock and all those things. And so it's been a really exciting time here the last few months.
I'll bet it has. Joe Betzwieser, how about you?
So I'm a staff scientist down here at LIGO Livingston. The stuff I've been most recently involved with include the calibration of the instrument. How do you know when we say that the motion at 100 hertz is something like 10 to the minus 19 meters per root hertz, that it's that to plus or minus 10% of the 1 sigma error bar. So making sure our statements are correct. I'm also work with the commissioning team to help improve the noise sensitivity of the instrument. I'm very familiar, for example, with a lot of the code that goes into running the instrument across various computing systems.
Great. And to finish off the introductions, Stefan Ballmer, can you tell us a little bit about how you participated in the project?
Sure. I also started as a graduate student back in 2001, and my role in this was mostly helping to put together the systems that everybody else assembled. That is, Brian and Brett and others put together the suspensions. Other colleagues put together the optics, the electronics, and taking that all together and making it work as an interferometer and actually make it work at the design sensitivity is where my expertise was in the last 15 years.
Okay, great. Thank you, all 5 of you, for kind of kicking things off by giving us an introduction. So I want to put a question to any or all of you. Feel free to jump in. I'm curious about what it was like that night back in September 2015 when the first sort of telltale signal was spotted, first and only, I guess, from these inspiraling black holes, as we now think. Where were you when you heard the news? What did you think first? Did you think, hey, this is just another drill, another blind injection, as they put it, or how quickly did you conclude that this might be the real thing?
So, can I jump in? Yeah. So, in our time zone here, it was at about 10 minutes to 5 in the morning when the event arrived. And then seven milliseconds later, it got to Hanford. So I was asleep. Our operator, we have an operator around the clock, and he fielded a call not long after, because they're automatic systems that scan the data more or less continuously to come up with candidates. And the main motivation for that is because we share our triggers with other kinds of telescopes, so that they have an opportunity to slew to that spot, to that fairly large region in the sky where we might have seen something. And so there's a little follow-up procedure that goes on after that happens. So by the time I woke up, there was already chatter about this in email and so on. And so in the previous runs, previous LIGO runs before we installed advanced LIGO, one of my jobs was to be the guy here who put in blind injections to fool people. And so I kind of had that in my head, even though I hadn't heard that they'd started in this run. And so so I became convinced over the course of several days, once I talked to certain people who might have been involved in that and made sure that there wasn't any kind of double secret blind injection going on. The routine injections they were verified that day pretty quickly.
Yeah, maybe I can jump in at this point. I also was working the night before till about midnight Hanford time, and yeah, I'm kind of glad I went to bed that night, to be honest. The next morning coming in, there was really a buzz at the observatory already, and everybody was wondering whether we knew whether this was a blind injection. But to be honest, the very first thing I saw that morning was the e-log entry stating in big letters that no, this was not a blind injection. Before I knew anything else about the event, I knew it was not a blind injection. So yeah, it was quite a surprise from that point of view. And we were lucky. I know at Livingston it was the same situation. People were thinking about working that night, and it's pure luck that they didn't.
They were working. They stopped not long before.
Yeah, I left at 4 a.m.
Yeah. They ran into software problems, so you should thank the software authors for those.
Brian and Brett, how did you find out and when?
So I actually found out about it about a day later, as the word started spreading around, and I remember, looking at the early versions of the waveform and then pulling up the USGS map of worldwide earthquakes to see if there was any kind of earthquake around, and there hadn't been one for about at least more than 2 hours before the event. I'm trying to figure out if there was some way that a glitch in the seismic system could have caused it, but the waveform was so unusual that I figured it couldn't be a glitch in the seismic system, and started thinking that it might be something real. The other thing that really surprised the folks here at Stanford, and we talked about a little bit, was that the waveform was not the kind of thing we were expecting from neutron stars. And neutron star, and spiral, those two things come around each other. That's been the sort of the standard signal that we've been talking about since we started on this program. But if you look at the frequency evolution of the signal, you realize it wasn't neutron stars. So that gave us a certain thrill that it might be something, that we hadn't, that no one had really seen before. So I remember feeling that, thinking that was pretty cool.
So I may be misremembering this, but I think I read somewhere that this signal came in within a couple of hours after the advanced LIGO sort of testing the real instrument run had begun, right? So incredibly early in the run. Is that not true? Okay. Disabuse me of that.
It's a little more subtle than that. So,
okay.
So we had just finished. We were sort of finishing up a multi-week. We call it an engineering run, but it was intended all along that the engineering run would kind of segue into the observational run when everything was working, and in fact, everything was working. So the detectors were both in a mature state, a well understood state, and so what there is some truth in what you say in the sense that we had not established yet a background rate for the detector, and so we had to do something that no one had really planned to do, which is an astrophysically interesting event right at the beginning of this. Not quite as close to the beginning as you had implied, but close to the beginning of a large multi-month stretch of data. We had to really do a hands-off detector and take data in earnest at both detectors to establish a background while the observatories were in the same state, a background that would support a claim of detection. And that's something that kind of caught us by surprise. And so here we had to cancel all the work permits. We even canceled the liquid nitrogen delivery at the following time when it happened, so that we could get as much data in the can as possible with essentially the same statistical properties as the detectors were when the signal came.
Okay. Now, another possible myth that you can dispel, but I had heard that no one was really supposed to know whether or not, no one was supposed to be able to determine whether or not this had been a blind injection, but it was sort of divulged very early on that it was not a blind injection. And so, in effect, the coverage you're giving yourselves, the test to which you're putting everyone was not in effect this time around. Is that true?
Yeah, because we were still in the engineering run, and we had not quite finished getting the hardware injection pipeline to a good enough level such that blind injection would have been couldn't be determined from, let's say, an astrophysical event versus somebody putting something into the instrument. There were still some artifacts we were trying to work out. So,
Yeah.
we were still in the engineering run. We had not started the blind injections yet. Because
one of the things that we were tweaking those last days was to establish that we could do those blind injections properly. So we hadn't quite established that when it happened.
I see. Okay, so not that it matters in the end. It's just that it sounds like it caught you all a little bit by surprise, which is cool. That happens in science sometimes.
In a good way.
Yeah, in a good way. Yeah. Okay. Well, we've got lots of questions coming in. So if you guys don't mind, I'm going to just start relaying some of them. And here's an interesting one from Ellen in Mankato, Minnesota. I hope that's Minnesota, not Montana. I'm so sorry. Ellen says, I heard Joe say 7 milliseconds in reference to the signal being detected in Livingston first and then 7 milliseconds later in Hanford. So is there an order to LIGO station detection as the wave hits the Earth? And can you explain that 7 millisecond delay?
So if a wave were traveling directly between one of the observatories and the other, there would be a 10 millisecond delay. That's the light travel time. And so so since it was less than 7, it meant that it was coming sort of off that line. So if we knew nothing else about the wave, we would be able to constrain it to a kind of a donut on the sky. But with additional information having to do with polarization and so on, we were able to constrain it a little bit further than that. So if it were coming from right overhead at both sites, then there would be no delay. It would hit both sites at the same time. So it's always between 0 and 10. If it's greater than 10, that's not a gravitational wave. That's what we think.
And this is part of the argument for bringing more LIGO detectors online, if I'm not mistaken, right? The more places you have doing these measurements, the more precise you can get about localizing the signal. Is that right?
Yes, and polarization.
Great. Okay. Let's see here. We have a question from Bob in Maryland who asks, what precisely is it about these gravity waves that is, quote, smaller than a proton by some popular press accounts? I think what he's getting at is that the precision of the detector has to be way smaller than the diameter of a proton in order to detect any change in the distance, right, within the LIGO arms. So can one of you explain why the precision has to be so high?
I could try to take that one. So the amplitude of the wave is really a ratio between how much the length changes divided by the length. That's in the case of an electromagnetic wave, the wave strength is the electric field. In the case of a gravitational wave, it's the relative length change. Now, for our detectors with 2.5 mile long arms, that relative length change for this event was something like 1/1000th of the diameter of a proton, a few times 10 to the minus 18 meters. That's the length change over the length change over our arm, which is 2.5 miles. And so that's what we had to measure, indeed, in that event.
Maybe to say that another way, the way that gravitational waves work is that it's a distortion of space-time caused by these accelerating masses, but that space-time itself is really stiff. And even if you put a tremendous amount of energy into a wave, as this event did, the actual distortion of space-time itself is really small. And so, since we're trying to measure that distortion, and that distortion is really small, as Stefan was saying, that's really what sets the challenge for us technically.
Okay, you guys are being super tolerant about these questions, some of which are coming from non-physicists like myself, but related to this, my understanding is that by clever use of mirrors and sort of sending the laser signal back and forth many, many times, you're in effect extending the length, the effective length of the two arms. So you're measuring a sort of a longer baseline. So when you say that you're measuring a change in length of something like 1/1000th of the width of a proton, is that the length over the whole sort of virtual length of these arms after you've sent the signal back and forth 400 times, or are you talking about, like, is that the actual length of the change in distance brought about by one of these waves? Does that make any sense?
Yeah, so the lengths relevant is the 2.5 miles of the arms. It's true, we actually bounce our laser beam a few hundred times back and forth until we read them out, but that's not the number we quote. So the displacement of the length distance between the two optics in one arm changed by the 1,000th of one proton diameter.
Okay. Another physics question for somebody to jump in on. Viola from Texas is asking, what's the wavelength of the gravitational waves that you guys detected? Does that question make sense? What's the wavelength of the wave? I mean, it might be a specific number that it wouldn't make any sense. But
yeah, I think we're all just trying to do the math in our head.
It's swept in frequency from tens to hundreds of hertz. So if you just say 100, when it was 100 hertz, you just 3 times 10 to the 6 meters, 3 million meters, right?
Sounds right.
Yeah.
Huh.
So it's a very long wavelength.
Long, but not incomprehensibly long. That's kind of interesting. It's like within the realm of human imagination. That's cool.
And that's how we get away with having all those bounces, because we can bounce back and forth a lot of times before the wave changes appreciably.
Okay. All right. This is a more cosmic or cosmological question, but it might be a fun one to answer. Coming in from Kevin in North Andover, Mass. What do I tell my non-scientific-minded friends and colleagues about the true cosmic significance of this monumental observation? So, I mean, to kind of boil that down, what's the big deal?
So there's some wonderful kind of things that sound like they must be exaggerations. In fact, when I first read them, in our paper drafts, it kind of blew my mind. Right? So when these two black holes, so there were two black holes that each was 30 solar masses ish, and then they combined and made one larger black hole. And our understanding is that about 3 solar masses disappeared into the form of gravitational waves in that process. So 3 solar masses turned into energy using E equals mc squared, essentially. But it happened so very quickly that the peak power, in other words, the energy delivered per second, exceeded that of all of the starlight in the visible universe for that tiny fraction of a second. And I mean, when I first read that, I thought that's kind of crazy. And then I heard Kip Thorne say it. In fact, as an experimentalist, I don't even know how to calculate that. What all the starlight is in the universe. That's kind of a big deal.
Absolutely.
Let me also jump in here. I mean, the other aspect of this, which is sort of fundamental in various points into the future, is that it really allows us to discover a whole new aspect about the universe. I mean, we sort of thought we were going to observe these gravitational waves first, and then we're going to slowly but surely learn something from it. But on the very first event, we established that there are binary black holes out there. We can observe the two merge. It follows Einstein's theory exactly until there is only one black hole left. And so I think for the future what that means is we have a huge potential of discover new things, and I'm sure a lot of them will be surprises. So I think that's sort of looking into the future, that's probably the biggest aspect of this.
Yeah, I would say that we're probing regimes that you can't replicate in any other way. So like this black hole merger was basically a test of GR in the strong field regime, which had never been done before. And so I mean, usually we're talking about like starlight being bent by like the sun, or like gravitational redshift, which are all kind of the weak field limit. Whereas this is a test of GR in a regime that had been probed before, which I think is quite interesting. And going forward, we're going to learn about things when we start seeing, let's say, neutron stars merge into black holes. We're going to learn a lot about condensed matter in regimes we can't probe on Earth as well, which I think would be very interesting going forward.
Yeah, just to underline that, the Monday after this, my colleagues from doing nuclear physics knocked on my door and wanted to know more about it, because suddenly that became relevant for their future. So it's really the potential is enormous there.
In the sort of zoo of astronomical events that we have imagined, is this binary black hole scenario sort of like the best possible one, the one that, like, it's the most mind-blowing one you could have imagined for a first observation from LIGO? Or are there more waiting, to, like, looking around the corner that would be equally mind-blowing?
So, I mean, as an experimentalist, the thing that would be most fun would be to get some theorist to say that they were wrong about something. And
good luck with that one, Joe.
So sadly, the people who are doing the GR simulations nailed it, apparently. And so we can only hope in the future that there's maybe some kind of cosmic string that doesn't work, or maybe the equation of state of neutron star is wrong in some way. But that's just me and my neuroses. I don't know what people want.
Okay, I'm gonna go to more audience questions. Let's see here. Has there ever been a more collaborative science effort than this one, asks Laura in Glen Falls, New York, so involving so many scientists across so many countries? Well, I think I know the answer to that. I think that some of the Large Hadron Collider experiments are even bigger, but this one was pretty damn big. How do you manage a thing like this?
It kind of snuck up on us. When the LIGO Scientific Collaboration made a data sharing agreement with the Virgo collaboration in Europe, that basically eliminated competition, which sounds bad at first, except that when you analyze all of the data together, at the raw gravitational wave together, you can do better science, because there's no delay in figuring out how the other side did their analysis to see whether you agree with it. And that, in principle, should allow us to generate triggers for other kinds of astronomy and astrophysics instruments more quickly and with better sky positioning. And so this is a case where essentially the science itself mandated that we all work together.
And I think we've been really fortunate to have such a collaborative group of people too. I mean, some of the collaboration, goes back, because as I was saying, 25 years ago when I was an undergraduate at MIT, I was working with Giaime there, and that kind of a close-knit collaboration, well, it usually works out for the best. Certainly in this case, but the broad data sharing, so that we know that everybody who's going to do the work will get some of the credit, helps a lot. And we spend a lot of time on the phone talking around. I mean, certainly being the lead scientist on one of the biggest subsystems in LIGO, and working not at either of the Caltech or MIT, the main labs, has been, it's been an interesting challenge to sort of make sure that you stay sort of closely integrated with the whole group. But it's a pretty friendly group of people, and so we've been able to make it work.
So Brian, and other folks, to that point about friendliness, we have a really interesting question from Ray in Cambridge, who asks, between September and February, was there any disagreement among researchers about what this signal meant, or about how to present it to the public?
Of course not. No.
No, all 5,000 emails agreed completely on what to say.
So most of the disagreements had to do with the vagaries of statistical nomenclature, and not there wasn't a faction that was saying this isn't a gravitational wave. Essentially, no one after several days went by, essentially no one was making that claim. Of course, a lot of people had it as their job to double check all manner of things. We have a checklist that I don't remember how long it is, many pages, that took many weeks to go through.
I think we were fortunate as a collaboration that the first signal that came in was so big.
Yeah.
If it had been a marginal signal, it would have been much more difficult. I think it would be much easier to make good arguments on both sides as to whether it was real. But this signal was really large, and so it helped. I think it helped put people's mind at ease. I mean, I think a lot of people were really nervous about releasing a signal before we were certain as to what it was, but nature was kind to us just this once.
I have to say I'm pretty astounded that the confidentiality held for so long and that the embargo didn't start leaking really badly until the last couple of days. I mean, there were tweets, there were stories strongly suggesting that there had been, positive signal, but basically you guys kept it under wraps pretty well until the actual announcement. So congratulations. So related to that, though, I have a great question coming in from Giaime in the UK. Who is curious about what the panel thinks about the media response. What headlines have you seen that were overblown, understated, or just wrong? So how do you think we in the media have done on handling this story?
Well, I guess I can say something. I think we all expected this to be a story in the media, but I know I was personally surprised by the magnitude of how much press there was about it, which I think is just is great. We were on the front page of the New York Times and a bunch of other newspapers, and I think a lot of us were really surprised and pleased with how much press and how well it was portrayed in the media.
Yeah, I think that by and large, the message was sufficiently simple. I mean, to the extent that gravitational waves can be simple. Gravitational waves from a pair of black holes, that almost all of the media outlets got that basic information right. And the things they got wrong or muddled were probably not very important. To me, one of the big surprises was that there are all these energetic people much younger than I am that in the collaboration that had set up tweets and other social media methods and worked really hard on that, and it hit. That stuff really hit that world, and I think some of the kind of the people who work in our various universities doing PR were surprised at how well all these young scientists were at doing that. It's kind of cool.
Okay, but nobody has like a favorite pet peeve or wrong story or just a real sort of.
There was a story in the German language website that claimed that our detector operators were asleep when the event came, which is certainly wrong. I'm still kind of hoping it was a mistranslation.
Okay, so a lot of people were asleep, but presumably not the people in the LIGO control room, right?
That's correct.
Okay,
yeah.
All right. All right, I have a couple questions that kind of relate to, if you will, putting the O in LIGO. So it's the O stands for observatory, and now that you've observed something, in a sense, LIGO really is an observatory, and we can kind of begin to think about what gravitational wave astronomy might look like going forward. So we have a question from Dejan in San Jose who asks, if one were to build a new LIGO detector with the most modern detection equipment so that we can keep doing gravitational wave astronomy, could you do it with a smaller arm length? Could you enable detection of this event with smaller arms, or better, if you have better detectors or better mirrors or better cryogenics, do we really have to build these gigantic 2.5-mile long arms anymore?
Yeah, so let me jump into that. The thing that limits LIGO right now fundamentally is the thermal noise of the mirror. That is because we bounce that beam back and forth every time. Every time we reflect off a mirror, we pick up these tiny vibrations of the mirror due to its temperature. So somehow we would have to get around that. Now, none of us are seriously considering making it shorter, mostly because we already have a 2.5-mile detector, and if we figure out how to make the mirrors better, then we would install better mirrors in it and see much further. That said, the other way around, making it longer, might work to get around that thermal noise, simply because you have to bounce less off those noisy mirrors. So a lot of our work now actually focuses on what's the way ahead, what kind of observatories can we build in the future, for the next century. What can we discover with what machines?
Yeah, and that's really one of the great things about having such a diverse collaboration, is that like folks at Stanford are working on cryogenics. I mean, that's what Brett does pretty much all day, every day. He's trying to figure out how to make the mirrors colder. But there's also a lot of expertise here about mirror coatings and trying to make those coatings better. And so by having a big collaboration, with sort of its tendrils into lots of research universities around the world, you can kind of pick and pull bits of good ideas from lots of places. So there are a lot of ideas about how to make the detector work better, and that's what I think a lot of us are thinking about bigger and better, not shorter and cheaper right now. That just sort of goes to our experimental bent, I think.
Yeah, sure. Well, so the hope is that you'll get different kinds of signals that would be illustrative of different phenomena, right? So we'll probably see more of these binary black holes, but hopefully we'll also see lots of other things. So I have a couple of questions relating to that. So I'm going to combine two questions, one from Don in Port Angeles, Washington, and the other from Larry in Austin, Texas. So how do we know that the signal originated with two merging black holes? Is that because it's the only scenario that explains that particular signal, according to the simulations? And then from Larry, did the waveform really show this ring down that was predicted to occur after binary black hole merger? And would you expect a different signal from something different, like two merging neutron stars or something?
So there's in the paper there's you were asking about what sort of things generated hot or warm discussion among the collaborators. In the paper, there are a couple of paragraphs of essentially a heuristic explanation of why we're sure they were black holes, and it's relatively simple to explain. And the reason why it was controversial is because some people would say, well, why don't you just refer to the detailed GR calculations rather than do this heuristic thing? Well, the answer is because most of us understand the heuristic thing. So when two compact objects are in spiraling, there's a function of the two masses called chirp mass that by measuring how quickly it chirps up in frequency, you know what the answer to that. You can measure the chirp mass quite accurately, but you still don't know what the individual masses are. You know that when the chirping ends, because the chirp ends when the two masses are touching, and then once you've measured those two things, you know you can figure out what the two masses are, and you can figure out how far they were apart about. And so that much mass, that close to something else with that much mass, without quite touching, can only be a black hole. And that's why we know. But the second question related to that is, did we actually see the ring down? The signal is consistent with a ring down, but we would have needed some more signal-noise ratio to measure the ring down independently of the in-spiral signal itself. And of course, that would be great to do that, because then we could compare the two sides and show an additional compatibility.
Let me jump in on that one, whether we saw the ring down. I mean, we clearly saw the signal peak and get smaller again. There's no question about that if you've seen any of those plots. The question is what we mean by a ring down. And the reason some theorists really want to measure the ring down is once you're in a regime where you can use perturbation theory to explain black holes, you can measure aspects that are predicted for this particular type of spinning black holes. And unfortunately, that approximation that this perturbation theory actually works only starts being good in a regime where we don't have any data anymore. So did we see a ring down? It depends what you mean by ring down. We saw the signal get big and smaller again. We're not in a regime where we could actually resolve that spectrum of black hole excitations.
Okay, so just to pick up on that question and to slot in another one. So would you expect to see completely different signals if you were observing, say, two merging neutron stars? And related to that, are there more signals that you guys are still in the process of analyzing? I mean, the LIGO is still turned on, I'm assuming, right? So there's data coming in all the time.
Stefan, want to take the first one?
All right, I'll answer the first one. So what's different about a neutron star is two things. First of all, its chirp mass is much closer to about 2 solar masses. So it's chirping up in frequency over a much longer time. And the signal we observe is much longer. And the second part is the moment they collide, that happens at a much higher orbital frequency. In other words, it happens about at 1 to 2 kilohertz of gravitational wave frequency. So it's a very different signal. It would sound very differently if you play it back when you hear it. But the other aspect that's different about it is because our sensitivity is best around 100 hertz, we would resolve more of the in-spiral phase and less of the actual merger phase. So maybe, Joe, you want to take the second part of the question?
And so here's where we have to be kind of, we have to be respectful to our collaborators. The only thing that we've published so far has to do with those first 16 days of common observation, which spanned more than a month of actual calendar time. We haven't published or said anything publicly about events other than in that period, and so we're all not allowed to spill the beans about any at all. We're not even allowed to talk about whether there are any beans in the rest of the time. The run itself ended in 12th of January, and so right now, although our detectors are in lock part of the time, the main goal right now is to make them better, find some annoying noise sources and see if we can eliminate them by reconfiguring things. And that should continue until the late spring at least. And then we hope to run again early next summer or late this spring.
Yeah, I should mention during that first observation run, we weren't actually at the sensitivity we were designing the instrument for. We have about a factor of 3 on average to go just to reach what we originally designed. So we all have our work cut out during this year and the following year to get there, and the payoff will be that we have a 3 times better signal to noise for any similar event, or cube that 27 more events to see with. So the fact that we saw something that early on really means our payback will be significantly bigger once we reach the design.
Okay, so that's okay. Read between the lines, then, folks. I have a really interesting question from Shen in College Station, Texas. Can one of you explain how LIGO is funded? And sort of even more interesting than that, how does the sort of success of the experiment with this detection change the prospects for funding going forward? I mean, you can imagine on the one hand that everyone would say, gosh, I'm so glad we spent $1 billion, let's spend another $1 billion and really, go even deeper on gravitational wave astronomy. And you can imagine other people saying, okay, we confirmed general relativity, let's shut it down and not spend another $1 billion. So maybe those are the extremes, but how do you go forward, and how do you make sure that the program stays healthy?
I think that, well, I should just say that the National Science Foundation has paid for essentially all of this in the United States, and the other countries we collaborate with, their equivalent funding agencies have paid for their bits. The Advanced LIGO detector has a lasers from Germany, and some of the important test mass suspensions are from the UK. But the NSF has been at this for 40 years or so, and so when I think of that, I'm just overwhelmed with gratitude to the NSF and the U.S. taxpayers for putting up with us for all this time. And until quite recently, we gave them essentially nothing. And so I'm really very, very grateful. Looking forward, I think that so many of the things Stefan referred to, although they require a lot of hard work and some new rework of the things that we have in terms of hardware, none of that is of the scale that the Advanced LIGO upgrade was, which is $200 million. Some of the more forward-looking things involving, rework of the test mass suspensions or new sites, of course, that would be much more expensive, and hard to talk about that really without any more specifics.
Yeah, and I think one looks at the astronomy case and thinks that things are good right now. I mean, I was at a talk last week by someone who does numerical relativity, and he was wondering why LIGO had never talked about black holes as sources, and was it because we didn't like black holes? And it's like no, it's because the number of black hole binaries that we knew about before September 14th was 0. Like, it's hard to ask for funding if, you know, the number of certain sources is this big, right? But now that we've seen those and we've gotten, you know, some better ties into the, doing real astronomy, you know, you hope that seeing some sources and getting some interesting evidence about general relativity and being able to point to particular improvements we can make and what kind of impact that'll have on astronomy will help the field move forward. That's what we're hoping for.
Okay, that's actually very optimistic and kind of ideal place for us to wind down since it's 4:45. So I want to say thank you to all 5 of you guys. Thanks so much to our alumni panelists from Stanford, Syracuse, Caltech, and LSU. On behalf of the Alumni Association and the program in Science, Technology, and Society here at MIT, I want to thank all of our viewers for tuning in to this Faculty Forum Online Alumni Edition. We didn't get to quite all of the questions that you guys submitted, but we'll pass on the remaining questions to our panelists and let them to respond at their leisure. You can tweet about this event and other MIT Alumni Association events using the hashtag MITAlum. And you can send us follow-up questions and feedback at alumnilearn@mit.edu. And keep an eye on the Alumni Association website for news about our next hangout here on Google. So thanks, guys. Really appreciate it. This has been super fun. Congratulations. Everyone's very excited and looking forward to seeing what comes next.
Thank you.
Thank you.
Thank you.
All right.
Thanks again for joining us. For more information on future MIT Alumni Association productions, please visit our website.